Okay, next let's talk about catalyst. A catalyst is a substance that simply provides a favorable environment, if you will, for a reaction to cause the rate of the reaction to increase. Now, even though the catalyst is involved in the chemistry that's occurring, in the end, it doesn't appear that it was consumed at all. And it wasn't. You'll have the same amount to start with and to end with. You'll have the same amount. Okay? So here's an example. So a catalyst can speed up a chemical reaction in a number of ways. So here's an energy diagram, right? This is an exothermic reaction since the products are lower in energy than the reactants. And so here would be the activation energy, right? So here's the activation energy for this uncatalyzed reaction. Well, let's say that we're reacting, I'm going to show you an example of this, where we react a ethane molecule with hydrogen. Well, if I use a platinum catalyst, what it does is it causes the activation energy to become smaller, and I'll explain why once we get to those slides. But it's going to cause the activation energy to be smaller. And so this is one way a catalyst works. It simply reduces the activation energy, now needs less energy to get up over that hump. So the reaction speeds up. Remember the Arrhenius equation, right? K is equal to A, that was that frequency factor or pre-exponential factor, e to the negative EA divided by RT. So if you lower EA, you're increasing the fraction of molecules with enough energy to react. So again, you're increasing the rate constant by using a catalyst. The second is to provide a completely different mechanism or pathway. So in this case, we're representing a single step, but that single step has a very high activation energy. But if I provide a different pathway where it could first do a single reaction that has a lower activation energy than the uncatalyzed, and then actually do a second step, but that second step still has a lower activation energy than the single step, well, again, I'm going to need a lot less energy to get from reactants to products, and therefore I'm going to speed up the reaction. So those are the two different ways, and I'll talk about this. This is like, we're going to see that in enzymes tend to do this type of thing here, okay? Okay, so the catalyst generally does not appear in the overall balanced chemical equation, although its presence may be indicated above the arrow, right? We always do that. So here's an example. You can catalyze the decomposition of hydrogen peroxide to water and oxygen by adding bromide to it, okay? We're going to find out that it didn't matter that it was hydrobromic acid. We could have used sodium bromide. It's the bromide in this particular case that's really important. Okay, so this is the overall reaction, but the mechanism looks like this. First, hydrogen peroxide molecules reacts with the bromide. Again, the bromide is coming from the HBr, right? That's a strong electrolyte. It dissociates into H plus and Br minus. So the Br minus is coming from the hydrobromic acid. That plucks an oxygen off of the hydrogen peroxide molecule to form the hypobromite ion, leaving behind water. But now this hypobromite ion is pretty reactive, and it's going to react with another. So this hypobromite that was created is now going to react with another hydrogen peroxide, and this time it's going to give up oxygen to it and release an O2 to form water and oxygen molecule. So this thing really, when it reacted, broke it up completely. And notice that we got our bromide ion back. So when we look at the overall reaction, we can see that the bromide, there's one on each side, so they cancels. The hypobromite ions on both sides, so it cancels. And what's left? Well, I have two hydrogen peroxides. I have two water molecules and one oxygen molecule. So there it is. There's our overall reaction. And notice that even though the catalyst was evolved in the chemical reaction. It never appeared in the overall reaction. Now, again, both catalyst and reaction intermediates aren't going to be found in the overall reaction. So how do you know which is which? A catalyst generally, there are exceptions to this, but not many. A catalyst generally appears first as a reactant and then is canceled later out by a product. A reaction intermediate always is first seen as a product and then is canceled out later on as a reactant. Okay? So this one is usually, almost always, this one is always. Okay, any questions about that? Okay, let's look at how a catalyst actually works on the molecular scale. Oops, no, not yet. Okay, so first there's two different types of catalyst. There's homogeneous catalyst and heterogeneous catalyst. A homogeneous catalyst is what you might think is all in the same phase. So the reactants and catalyst, again, all in the same phase. So we call that homogeneous. They could all be liquids, they could all be solids, but they all have to have the same phase, okay? That's a homogeneous catalyst. A heterogeneous catalyst, on the other hand, the catalyst itself is going to be a different phase than the reactants. Usually, a heterogeneous catalyst is a solid, and the reactants are either liquids or gases. Now, for the catalytic reactions, it's expected to occur at the surface, right? Because it can only absorb to the surface. It can't get to the middle of the solid. Okay, now maybe eventually it could diffuse into the solid, but that's a totally different story. And that's usually not the way catalysts work. It's usually just absorption of molecules to the surface of the catalyst. So here's an example. Here's the reaction of ethene. So that's a double bonded carbon, right? So there's a double bonded carbon and then the hydrogens, two hydrogens on each carbon. Well, that will react with hydrogen to produce, and I should show the chemical reaction for this. So basically what you have is you have C2H4 reacting with H2 on a platinum catalyst to form C2H6. So what happens is that the ethene molecule, which has a double bond. Now remember what a double bond is. It has a sigma bond, so that's direct overlap between the axis between the two atoms. And then the pi bond, which is the overlap of atomic p orbitals, right? Those atomic p orbitals are sticking out above and below the plane of that bond. And it's the overlap of those p orbitals that create your pi bonds. Well, those p orbitals are attracted very strongly to platinum atoms. So it causes this ethylene molecule to actually stick to the platinum surface. Hydrogen's actually the same way. Hydrogen likes to stick to platinum surfaces. Now, once they stick, it starts to weaken the pi bond, right? In fact, the pi bond's nearly destroyed. Now, basically, all you have is a sigma bond. And the platinum literally destroys the hydrogen-hydrogen bond to form two individual hydrogen atoms. And you can actually look up YouTube videos using, they used a scanning tunneling microscope, and you could see these hydrogen atoms literally skating around on the surface of the platinum until they finally find one of these carbons, which now doesn't really have a double bond, but we know carbon likes to have 4 bonds. So this hydrogen will attach itself to the carbon. And again, this guy's going to fly around the surface until he finally finds the other one. Now, once that occurs, there's no more pi bonding, And so the molecule immediately releases itself. The ethene molecule releases itself into the gas phase. So this is how it simply lowered the activation energy. It weakened the bonds. By weakening the bonds, you lowered the activation energy. Okay? This would be representative of heterogeneous catalyst. We have a solid catalyst and gas phase reactants. Okay? Okay, so again, and as you can imagine, as you increase the surface area, how many platinum atoms, increase the number of platinum atoms that the ethene and hydrogen can come in contact with, well then yeah, you're going to increase the rate. Okay? To a certain point, right? At some point, that it doesn't matter how much you increase it. As long as it's there, it's going to happen. So that would be 0th order. So we always assume that when we have a solid catalyst, we add more than we need. Therefore, the catalyst is going to be 0th order. Okay. Enzymes work in a kind of provides a different pathway in a way. What happens is that we have the substrate. So this is the molecule that's going to react. And then here's our enzyme. And they have very specific shapes. And not only do they have specific shapes, they have very specific functional groups as well. So what happens is that this molecule, this substrate, is going to find the enzyme. And this enzyme will only accept certain molecules, again, mainly dependent on their shape and their functional groups. And it's going to bond with that substrate. Then, within the enzyme, it knows to start performing other chemical reactions, which causes certain bonds to break. Once those bonds break, the intermolecular forces are no longer similar, and the molecule is allowed, the new products, right? The substrate in this case just broke in half, is now allowed to escape the enzyme and continue on. So the enzyme is basically, it's reducing the activation energy, but it's kind of providing an alternative reaction pathway for this to occur. So this might have multiple littler activation energies because it's going to be multiple steps instead of a single step of this molecule simply going from the substrate and falling apart by itself, a unimolecular reaction. Okay, any questions on how enzymes work? Okay, that's it for this chapter. We still have some time to go. We still have